Hello everybody, welcome to the Engineering Geology Webinar BE channel. In this channel, latest geological and geotechnical insights applicable to various projects such as mining engineering projects, civil engineering projects, water and irrigation development projects will be discussed. My name is Dr. Birhanu Ermias and I am an assistant professor of engineering geology and freelancer as geological and geotechnical expert. Today we are delving deep into cube slope method to understand its implementation. If you have ever wondered how cube slope method is quickly implemented in the field, you are at the right place. However, before we delve deeper into its implementation, let us briefly address a key point about the scope and the limitation of the cube slope method. In our previous episode 2, we said that cube slope method is not designed to tackle large-scale slope problems. Therefore, we have to understand the factors governing large-scale slope problems. Let us see factors governing large-scale slope stability. One of the factors governing large-scale slope stability is stress condition in the slope, including groundwater effects. This is one of the factors that govern stability condition on large slopes. When we say large slopes, by the way, it may be a slope with a slope height up to 600, 500. These are large slopes. And the second governing factor for large-scale slope stability is geological structures, particularly presence of large-scale features. And the other one is pit geometry, is also the governing factor for large-scale slope stability. And the fourth factor is rock mass strength. So groundwater condition effect can be determined based on the hydrogeological condition of the site, and the geological structures, particularly presence of large-scale features, could also be determined based on geological mapping, and pit geometry can also be optimized for the safety. The challenge with the large-scale slope stability is related with rock mass strength determination. Rock mass strength determination for large-scale slopes is difficult, very difficult. Strength of large-scale rock mass is very difficult to assess because most of the rock mass classification systems are used for assessing strengths or the rock mass condition, the property of the rock mass over a limited area or slopes. So there is no a good technique that help us to determine strengths of large-scale rock mass. So it is very difficult to determine. Since it is very difficult to determine, so large-scale slope stability is also complex. The failure condition is also complex. And the other challenge with large-scale slope stability is that the mechanism behind large-scale failures are not well known, just like other small failures. The mechanism of failure for large-scale failures are not well known, in particular for hard and strong rocks. The third problem related with large-scale slope stability is criteria for the shape and location of the failure surface are also not available. The other thing is most of the rock mass classification systems provide support measures and reinforcement measures for stability of rock slopes. However, the support measures are not feasible for large-scale slope stability. Among the remedial measures used for large-scale slope stability, only drainage is feasible for controlling the stability of large-scale slopes. So we have to know that in real life, most of the time, the dominant failures are local failures, therefore small-scale failures. Therefore, cube slope is designed for small-scale slope failures that includes from it may go from less than 5 meter height to greater than 250 meter height. To see one further example on large-scale open pit slopes. One example is, for example, the Aitik open pit copper mine in Sweden has the slope height of 555 at the deepest point. It has 555 meters. This is a large scale open pit copper mine. So for this type of large scale slopes, for the benches and the bench face slopes, it is possible to apply Q-slope, but for the overall total slope stability condition, Q-slope is not intended to be applied for such type of slopes. So for what's the solution for large scale projects? Future research in the field of large scale slope design must focus on quantifying the mechanism of large scale slope failures. So further research is required in order to handle large scale or total failure of the total slopes, but for local failures or bench face slopes, it's possible to apply Q-slope and also other methods, but for overall slopes, further research is required, and this research has to focus on quantifying the mechanism of large-scale slope failures and also developing better and more reliable methods for determining strengths of large-scale rock masses, because there is no reliable method for determining the strengths of large-scale rock masses. Without this determination, it is not possible to accurately predict the stability condition of large-scale rock masses. So when we come to the Q-slope, Q-slope is very useful because most of the slopes that we face on the engineering sites or different projects are not very large scale. Most failures are related with local failures as dominant failures. Therefore, Q-slope is very useful in order to handle this type of failure. So we have to see in detail about Q-slope. So Q-slope is designed such that it suggests stable maintenance-free bench face slope angles. So the aim of Q-slope is to suggest stable maintenance-free bench face slope angles. It avoids the cost of the maintenance costs and also support costs. This Q-slope is developed based on a simple correlation between Q-slope value and long-term stable slopes. So Q-slope is a value that is determined, that is a method that is developed based on the correlation or relationship between the Q-slope value and the long-term stable slopes of various projects. It is applicable to slopes ranging from 5 meters to more than 250 meters in height, and this correlation developed for Q-slope, based on which Q-slope is developed, are based on trials at several civil engineering and mining projects in Asia, Australia, and Central America. So cases considered for development of this technique are from examples taken are from Asia, Australia, and Central America. So trials are not taken from Africa. So we have to apply it in Africa also, see its applicability. So in order to understand Q-slope method very well, since Q-slope value is a value that can be calculated using parameters, you need to understand the parameters that are used in Q-slope to determine the Q-slope value. So Q-slope is designed such that it is stable maintenance-free bench face slope angles. Bench face like this. This is the bench face. This is the bench face stable slope angles. Bench face stable slope angles like this will be determined using the Q-slope value. In order to determine the Q-slope value, we need to determine first the parameters that are required to determine the Q-slope value, and there are 9 parameters, and we will see these parameters one by one. The first parameter used in determination of Q-slope value is rock quality designation. Therefore, what you need to know is you need to know what rock quality designation is and how to determine it on site. I will explain this in detail one by one. The 9 parameters, I will explain it one by one. So yes, you need to if you tune to this episode and also all the episodes, then you can easily understand how to determine all of the 9 parameters and how to implement it on site. And anyone who has gone through all the episode will be able to apply this technique, because I will discuss it in such a way that you understand it, understand each parameter, how to determine it on site actually. So the first parameter is RQD. RQD means rock quality designation. It can be determined on site based on visual observation. Very easy method. I will show you the easy method. The second one is the second parameter required for Q value determination is known as joint status number. How to determine the joint status on site, this also I will explain it in detail. The third parameter is known as joint roughness number. How do we get the joint roughness number on site after when the ground is, or the rock mass is excavated? So the site engineer will have the observation of the excavated surface, and he can determine RQD, joint state number, and joint roughness just from the observed apparent condition, ground mass condition. So I will explain this one also. The fourth parameter is known as joint alteration number, and how do we get this number also, I will explain this one. The fifth parameter is known as environmental and geological condition number, and how do we determine this also, I will explain this one. The sixth parameter is a part of it is known as strength reduction factor. There are 3 strength reduction factors. Strength SRF, strength reduction factor, APC. So there are these 3. One of them is strength reduction factor A, is the 6th factor. So this is the physical condition number. How to determine this number also will be discussed. The 7th factor is strength reduction factor B, strength reduction, stress and strength number. This is the ratio between the stress and the strength of the rock mass. This also will be discussed. The 8th factor is stress reduction factor C. This is related with the major discontinuity number. How do we get this one also will be discussed. The 9th and final factor is known as parameter is known as O factor. This is an orientation factor for the ratio between joint roughness, and joint alteration. So in order to implement or apply Q-slope system, what you need to do is just understand these 9 parameters, and you need to understand how to determine these 9 parameters based on your visual observation while excavation is undergoing on site. After the rock is excavated, the real nature of the rock will be visible. So the site geologist, engineering geologist, or geotechnical engineer will have the observation and make the necessary measurements on site, and then you can it is possible to determine RQD value. It is possible to determine joint state number, joint roughness number, joint alteration number, environmental and geological condition number, and strength reduction factors and orientation factors. These all 9 factors can be determined, and I'll explain each one by one in detail, so that you will be able to understand it and also implement it on site.